Hello, I'm Ben Baumgartner from Lockheed Martin in Sunnyvale, California. I am from Process Control Engineering. Our responsibility is electrostatic discharge protection for the facility here. What we're going to do today is go through ESD training along with some demonstrations, and we have here equipment to help you understand the principles of ESD, and here's the paraphernalia we have to give you some interesting demonstrations later on in this presentation. We're going to cover here is what is ESD. We'll define it. We'll tell you what EOS is, what their sources are. Then we'll go on to the controls here at Lockheed Martin, and this stands for Lockheed Martin Missiles and Space. We will then show you some damage mechanisms, and the final portion of this will be covering what our requirements are for superstations, which are for the very sensitive field sensitive devices that we are having in our facility at this time. First, let's go through some definitions so everybody knows what we're talking about. When we talk about EOS, this is electrical overstress, and that is damage due to exceeding the electrical capabilities of a device. This is when you damage something by overstressing it, you will take and exceed its parameters. If you change its parameters or if you destroy it completely, that is electrical overstress. Electrical overstress can be things like taking a 12-volt car bulb and putting it on 110 volts. It will act like the old-time flash bulb. That is electrical overstress. It could be from putting your battery in your electrical device backward. There are a lot of things that will cause electrical overstress. Electrostatic discharge, that is a specific event, and that event results in a sudden release of energy, generally in a very short period of time. Because this is a specific definition, by definition is a subset of electrical overstress. There's another term we use quite often. That's called tribocharging. Some people say triboelectricity. There are a lot of words using the word tribo in front of it. And tribocharge or triboelectricity is due to charge separating from the contact of two materials. Whenever you have two materials contacting each other, the charge is separated, and when you separate the materials, now you will be able to see an electrostatic field, and you've increased the potential for it to do damage. Some additional terms that we'll be using is discharge or ESD damage, and that can be arrived at by a transfer of charge due to an arc. That's the type of thing that you can feel sometimes when you slide out of your car and touch the car door. Transfer by contact, which you normally don't feel. You touch things when you have a slight voltage on it, you will not feel that transfer. And the hardest to understand and does damage only to certain types of devices is the transfer due to induced fields. We will cover all those things. The induced voltage is electrostatic charge caused by polarization. There are two devices in the electrostatic protection world that we have to be concerned about, and that is the voltage-sensitive device and the energy-sensitive device. The voltage-sensitive device is damaged by electrostatic fields, or can be damaged by electrostatic fields, and is definitely damaged by a direct discharge, this transfer by an arc. The energy-sensitive device is damaged only by a direct discharge or contact. In other words, you have to put energy in to destroy the device. Where in the device that's field sensitive, you do not have to put in a lot of energy to destroy it or even damage it. There are some other terms that we need to know that we use quite regularly, and Everybody understands what insulative material is. Well, we have a definition for that. It's a very high resistance material that does not dissipate charge. In other words, if you charge up a piece of Teflon, the charge will stay for a very long period of time because it has an extremely high resistance. In electrostatic discharge protection, we have a material called dissipative, and this term is used throughout in the terms of protection for many types of materials, devices, and etc. The resistance of this material results in a slow discharge of energy, and that is the ideal situation for protective materials. Of course, there are conductive materials. Metals are conductive. There's a lot of other materials loaded with carbon that are conductive, and the resistance of this material results in a fast discharge, which is generally not what we're wanting. In terms of all these insulative, dissipative, conductive, we use the definition of conductive or conductivity as any path, as a path for any amount of current. Therefore, if you have an insulative material, it has a resistive path to ground. At extremely high, will not transfer much current. Dissipative will transfer more current, and conductive will transfer a lot of current. So we will use the term conductive for dissipative materials and even for insulative materials, and you have to understand the context it's being used in. Conductivity is an engineering term that has specific definition, but it will be used here interchangeably with conductive and ignoring the definition that the engineers use. We talked about direct discharge. An arc is a direct discharge between two objects. It can come from or be exhibited by two different modes. A corona discharge is a local discharge of electrons. You won't have a blue color spark going between the two objects. You'll only see a little glow on the end of the needle, and ionizers use this corona discharge. If you have a very high voltage on a person, you might have some corona discharge before you have a arc, which is a concentrated flow. This is the one you hear and feel if it's high enough. Contact, of course, if you touch something and you have a voltage on it and you have resistances that allow that charge to be transferred, by contact you will transfer charge that you won't see or hear anything, but you will still be able to damage devices. We're going to represent a person by a sphere that has a certain charge on it. And if this person touches a device, they can have an arc going to the device, and if the device is grounded, the charge will go to ground. Here this is represented in this diagram by an arc to a device. It's represented by a resistance going to ground. Whenever there is an arc or contact, current will flow through this device, and the current causes the heating, which causes the damage if the conditions are right. The contact of the person to the device is a much lower resistance contact, but it's generally a lower voltage, so it can or cannot be dangerous to the device. We talked about tribocharging. This phenomenon needs to be explained a little bit. There are two types of charging mechanisms depending on what is being moved. If you look at charge transfer based on an insulative material that is the base here, and you have a conductive block, you have one type of transfer. If you have a conductive material and an insulative block moving on there, you have another type of transfer. What this tells you is that if you have charge transferred the minute you have contact, and you slide this along an insulative material, this charge cannot move, because we said insulative materials have a very high resistance. Therefore, the charge doesn't move down here. Charge can keep transferring off this surface onto that surface, and eventually, when we take and lift it off here, we have a high field on this metal object. Excuse me, on that one up there. If we take an insulator and slide it along, then the conductor here allows charge to move, so the charge will move along. It moves underneath here, and when you move the insulator up, you will have a charge on the insulator. You will also have a charge on the metal. These charges are equal and opposite, but there won't be any charge back on the metal here until you lift it off, and then charge will distribute itself back over again on the metal portion. You notice ground is not involved in here. Ground, a contact to a ground by the metal does not take and prevent tribocharging. What it does do is take the charge off that is put on the device. We will go over to the table now, and we'll pick up some devices to show you that in a more explicit fashion. First, we must define what a capacitor is and understand how it stores energy. If you have two conductive surfaces with an insulator between them, which can be air, this is a capacitor. The capacitor has the ability to accept charge. When charge is placed on the capacitor, it raises the potential of these two surfaces. This creates a strong field between the two surfaces. This strong field, when it gets strong enough, is what causes the discharge between surfaces. It does the damage because of the amount of energy stored. The energy storage can be looked on as like a battery. The more the energy is stored, the greater the potential for doing damage for electronic devices. Now, let's see how this relates to tribocharging and capacitance. To understand tribocharging, we have to understand the concept of capacitance. What I have here is two metal plates. These two metal plates have capacitance between each other and a certain value. But one metal plate also has capacitance that people don't realize. This capacitance, the other metal plate is the world around them. It's me, it's the floor, it's the ceiling. So one object can have a capacitance. And in the tribocharging instance where we talked before about the surface being insulative, I have a piece of Teflon here, and to illustrate that example, when I put this metal plate down on the Teflon, it has picked up charge. If I slide this along, as I explained earlier, the charge will stay on the insulator. Now when I lift it up, this has a capacitance, and there's a field line going back to the Teflon, back to me, back to the world. It's this field that is a potential source of damage to electronic devices. If I assume now that this is a metal surface and this is Teflon, when I put it down, I have the same two contact surfaces and electrons will be transferred. But this time, if this white sheet is a good conductor and I slide it along, the charge will move along underneath it, and therefore the same charge that I had over in this end of the piece of metal will be underneath it here, and I lift it up, and now there's charge on this insulator. There's one more thing that we have to address in relationship to tribocharging, and that is humidity. The issue of humidity affects the tribocharging in materials when there's a lot of moisture in the air. For example, if you have a insulative material and the moisture in the air settles on it, there is a phenomenon called bleed back. The charge now runs along the surface as it does with a conductive piece of material, and this reduces the amount of tribocharging that you see. Therefore, on very dry days, the surfaces will be very dry and have a high resistance. This allows the charge separation to stay where it's at and increases the amount of tribocharge. On moist days, the tribocharging is much less because of the bleed back phenomenon. Therefore, on dry days, you have to be extremely careful in handling material so you do not charge up the material and cause a hazard. Our program is designed to protect you from ESD in all humidities. To continue on with tribocharging, we need to talk about charge separation. If we take a ESD bag and put it on conformal coating, we have charge separation. In other words, tribocharging or triboelectrification. If we take and raise this bag off of that conformal coating, we have charge separation, and as I said earlier, once you separate those two objects, you begin to see a field. To demonstrate that, we have a piece of equipment which I will show you shortly that measures the charge on this system. And when you set the bag down, you will have very little voltage seen on the system. The minute you lift the bag off the surface here, you will see a charge. When you put the bag down again, the charge is close together, therefore the fields are not available to the rest of the world, and now you will go back to the 0 point. And you can lift it off and it'll charge up again, so you have this continual up and down as voltage as you move it around. In effect, you're changing the capacitance of this object in space, and the fields are coming from the material out into the world, which is the thing that is dangerous for ESD sensitive devices. I will now explain the equipment that makes the measurement over here that's on the table. This is the main unit of the electrometer, and the electronics in here decides what voltage it has to provide to the electrometer head. Once it makes that decision and outputs on the meter, we also are recording it on the chart recorder here, and we have 0 volts here at the center. It goes up to plus 2 kV, which is 2 kilovolts, and minus 2 kV, and now we see an output of what the voltage is on the electrometer head. Now we need to explain how the electrometer is calibrated. The electrometer system is calibrated with a power supply, which we have here, and this power supply is connected to what I call a resistive wand, which is a 10 to the 8th ohm resistor to prevent people from getting electrocuted from a high current. And we can show the calibration now by setting this power supply at 2 kV, and we come over here and touch the electrometer head, and now when I flip it on, it goes to minus 2 kV. If I turn the switch to plus, it goes to 2 kV plus, and if I remove the wand, that voltage stays there. That is the electrostatic voltage, and you notice that I can touch ground on the case here and put my finger on the plate and ground that voltage without any sensation of charge. This is how we calibrate the system, and we have a scale here in which we can change it to plus or minus 200 volts, and we'll be doing that during the demonstration. Now that we've explained the instrumentation for measuring electrostatic charge, let's go back to our charge separation demonstration, where we're going to show that when you separate materials, the charge shows up and then disappears again. Now we'll go over to the electrometer, and we have here a ESD bag and a conformal coating that's on the plate, and I will put my wrist strap on to ground myself, and I will now take and push down on the ESD bag and the conformal coating to make sure there's contact, and when I lift it, you'll see there's a little bit of charge. Now if we change the scale to a 200 volt scale, you'll see that there's charge, and if I put the bag down, the charge goes to 0 apparently, but it's still separated because I lift it up and the charge is back again. So you see, any time that you take a metallized bag with a conformal coating against an insulator, we have this tribocharging effect, and we have the charge separation, and that effect is present in any of your materials at your workstations. Now for the next subject of induced charge. The factors with induced charge are that the person, as we've talked about earlier, has some capacitance, and as he gets closer to a device, he will induce more charge in the device. This is represented by this capacitance C here, and as we said earlier, any object in space has capacitance. The capacitive coupling is determines the amount of charge induced into the device. In other words, the amount of polarization. The capacitance is larger because the area is larger, then more charge will be induced in the device. If the capacitance is a greater distance away, there will be less induced voltage in the device. So the two factors are area of the surface that is coupled into the device and the distance that the area is away from the device. When you couple into a device here that has a resistance, what happens is charge will come up from ground to satisfy the charges that you are inducing in here. That's polarization. When that charge runs through the device, it will cause a little bit of heat. If this device is an energy-sensitive device, as we explained earlier, it is not sensitive to fields that are induced by this polarization effect. Therefore, that device won't be hurt. If we have here extremely high resistance and we induce a field in this, current starts to go through that device. But if the resistance is an extremely large number, we're developing an extremely high voltage across that, and with the voltage-sensitive devices, this device is essentially an insulator, and the insulation will break down. That is field-induced damage on a voltage-sensitive device. We have a demonstration here which will demonstrate the fact that you can charge an object from a styrofoam cup and induce a charge in the object. What we have is a conductive sphere which will be a gold-plated ping pong ball, and we will put this sphere and drop it into a charged styrofoam cup. When we drop it onto the electrometer plate to see if there's any charge gained by the gold-plated ball, and it bounces off of here, you'll see that the needle doesn't move. If we take the gold-plated ball, place it in the cup that's still having the same charge, but we maintain a ground contact, and then drop it on the plate, you'll see there's a charge. Now, why is this important? What this tells you is that anytime you induce a charge on a circuit board and you ground a conductor on that circuit board, you can induce a charge in it. So this leads to the conclusion that you want to maintain very little contact with a circuit board. You want to minimize that contact. And we will go over here and demonstrate this by the use of a styrofoam cup and a gold ball. And first I have to ground myself. And we'll check that we're still at the 2,000 volt range. I will rub the cup, and part of this principle is to demonstrate that the cup has a lot of charge on it. And you notice the cup is sitting on the electrometer. The charge is negative. It's even gone off scale. And when I lift it off, it comes back to zero. This means that when I place the gold ball in the cup, there's not going to be any charge coming off an insulator. This is a very important fact to recognize when you were talking about charged surfaces and the distance away from a sensitive part. I'll now take the gold-plated ball. I will drop it into the cup at a distance, and now I will take and try to drop it onto the cup, and you see there is very little change in charge. I will now take the gold-plated ball, place it in the cup while I maintain contact with it, and now I have induced a charge into that gold-plated ball that's available through my wrist strap and has come up onto the gold-plated ball. Now, when I roll the ball out, it has picked up charge, showing that I can induce a charge in a grounded object if I am in a strong field. And this is a principle that you have to watch for when you're out in the shop, and try to maintain very little contact to tribocharge surfaces of circuit boards. We have just seen that grounding doesn't necessarily give you complete protection. Nevertheless, we use grounding as a very important tool in keeping static charges from developing at a workstation. We will cover in the next few slides the use of the ESD common point ground, describe the third wire on the AC outlet and its relationship to ESD grounding, talk about vehicle ground, building grounds, where they're attached, equipment grounding and how that is important, and soldering iron grounding, which is at a lot of the stations where equipment is assembled. Now let's talk about earth ground and grounding issues. Many people believe that you need a earth ground at every station. That is not necessary. A grounding rod has resistance, as you see from this chart. It is not 0 ohms to ground. The grounding resistance depends on the length of the rod, moisture, and other factors. What we do at a workstation is we use the third wire ground as the ground point to establish the equal potential at the workstation, and this is connected back through earth where the power company supplies the incoming power at the building. It's very important that the ground be maintained, and this is what the process control certification does. I have here a little checker that can be bought at hardware stores, and if we plug this in, you'll see 2 green lights. This tells us that the equipment grounding conductor is connected, and it also says that the polarity of the neutral is proper. These are important items because there are a lot of times when a socket is miswired or there is no connection. This connection is the point that the station uses to ground charge at the location, and that is all that is necessary for the proper ESD station control of ESD. Personnel grounding is the most important way of keeping ESD from damaging parts at a workstation. The wrist strap is connected to the common point, and we have a wrist strap here that has a certification sticker on it. That is very important that you use a proper wrist strap that has been improved. We have leg straps that are used in certain areas. They're only good if you have an ESD floor, and that ESD floor must be certified. The wrist strap connection can be made to the vehicle. If you have a vehicle that is in an assembly area, that vehicle is grounded to the equipment grounding conductor through the building ground. We never allow contact to occur from an ungrounded person because that person may place charge on the person that is grounded, and we will explain that later in some demonstrations. If you have to make contact, if you have to deliver something to a person, set it on the ESD workstation. That takes the charge off of it, and therefore, if you're not grounded, you won't have any problem with putting charge in the person that is working on equipment that may be touching a sensitive device. This slide shows schematically what goes on at a workstation. We have a table mat that can have a resistor in there to limit the current going to the common point, but it's sufficient to drain off any charge from equipment or any tools you put on there. It is connected to the equipment grounding conductor. If you have a shelf that you need, it is also connected to that point. We do not use shelves here very much because we believe we should package the device if we're putting it up for storage for any length of time. The wrist strap connections here go to this point, and all that is connected to the equipment grounding conductor, which is connected to the building. The floor mat here is connected to that point. The only thing that isn't connected is the ESD floor, which is connected to the equipment grounding conductor through the building connection. This equipment grounding conductor is at the same potential as the building ground, and therefore you do not have potential differences between any of these objects or pieces of equipment if they're all connected up and certified. We talked about charge being transferred from an ungrounded person to a grounded person. The wrist strap has a resistance in it to ground, and this resistance limits the current that is going to ground. It also has the effect of making the charge placed on a person take a little while to get to ground. So if we demonstrate here that a person will transfer charge from one person to another, that charge is instantaneously transferred because there is very little resistance between two people, where the wrist strap to ground of the grounded person has a 1 megohm resistor in it. Therefore, because the resistance is low, when one person makes contact with another, that voltage is transferred over to the other person because the charge transfers extremely rapidly. What we're going to do is charge up a person with an electrometer, and we're going to charge them up to 2 kV, and this person represents about 150 picofarads capacitance, can be more or less. He goes over and touches another person. What we have here is 150 and 150 picofarads. The sum of those is 300 picofarads. So by this equation, charge is equal to the capacitance times the voltage. Means that if we have a charge on this person and we transfer, the capacitance here now has doubled. That means the voltage has to go approximately to 1/2 of that to equal the same charge. Now we'll go over and do that demonstration. Now let's demonstrate this charge transfer between two people. I will take and remove the electrometer plate, place my wrist strap into the electrometer, and charge myself up to 2,000 volts. Now we'll ask for a volunteer to come in and touch me, and you'll see that the charge is approximately split between us, and the resultant voltage is nearly half of what we had when we started this experiment. What this shows is that the charge is transferred from one person to another very quickly. If that person is a grounded person at a workstation, that voltage will be on that person before the wrist strap carries the voltage away. At the workstation, the third wire ground, besides being used to ground the person, is also used to ground electrical equipment. Electrical equipment can have leakage currents, and that's really an electrical overstress problem. An example is a soldering iron. The soldering iron has capacitances that couple voltage into the equipment, and since the equipment uses the third wire ground here to ground that equipment, that current does not show up as a voltage should some small current leak across things in the equipment. The resistance is checked on the soldering iron, and you have to check that depending on your particular programs and the types of irons that you have. And that assures that the iron will not cause any damage to sensitive components. Another important part of ESD protection is packaging. We have some packaging principles that we follow. We'll talk about the types of packaging material, we'll define what a primary package is, and we'll talk about the labeling that needs to be on packaging to identify that there's an ESD sensitive part in there, and we'll talk about the packaging of very sensitive devices. The MIL B 81705 specification has established the different classes of packaging material. The first type is a waterproof electrostatic packaging that has a metal foil. It has strength materials built into it. It has a dissipative polyethylene material on the inside. The metal foil on the material provides excellent protection from electrostatic fields. This is a type of packaging. You can see the marks on the edge here showing the strength. The inside has a dissipative coating and satisfies the requirements for the military specification. The second type of packaging is the Class 2, Type 2 packaging, and that is a dissipative pink polyethylene. It can have a dissipative coating on the surface. Most of the polyethylene material that's out there has a surfactant milled into the surface, and it bleeds to the surface, it picks up moisture, and this is what gives it its dissipative properties. This is the pink polyethylene material. It allows it to be sealed in this, what makes it into bags. They take material, flat material, seal it on the edge. It is transparent. It is not highly capable of shielding fields, but it does protect very well against direct discharges. The third type, the Type 3 or Class 3, is a metallized foil bag. It may have one or two layers, generally just one layer. It has different types of materials built into it for strength. It is also fairly transparent. This bag, because of its metallization, is conductive and will shield somewhat compared to the pink poly, but it does not really protect voltage-sensitive devices. The primary protective packaging is defined as the innermost package that fully protects a device. There are many forms of bags and types of packaging that can do that. Tote boxes here are a primary package if they're enclosed. The lid has to be on them for them to be a primary package. The electronic equipment box that has the electronics in it, if it's a metal box with the connector caps in place, is also a primary package. And there are other carriers and blister packs that can be used for electronic packaging, and you have to determine whether those are sufficient for giving primary protection. The packaging is part of the protection and handling of material using proper packaging needs to be followed. If you don't handle material when you have it improperly packaged, if you handle material that's improperly packaged, you can damage it. The material has to be packaged properly before you can handle it. Conductive materials such as the Type 1 and Type 3, that is the metal foil and the metallized bag, are very conductive and need to be removed from the certified work surface after you remove the part from them to work on them. Also, a very important handling procedure is minimize the contact on insulators, because you can tribocharge the insulators where you touch. The handling of cables and connecting cables need to be done according to the specifications. The engineering must be aware of the problems here and need to specify how that is done. All the packaging that you handle in terms of ESD needs to be identified that there is sensitive devices in them, and you need to follow the proper specifications. Now to do a demonstration relating to handling issues. We said that cables connected up to a box, and you remove the proper packaging, the connector cover, and you connect up the cable is very important. We have here a piece of material that has an insulator on one side and a copper conductor on the other side. What I'm going to do is use this to represent a coaxial conductor that is covered with an insulator on the outside, and the electrometer will be the shield around the coax. If I set this down here, now I have a conductor going across a surface that is the outer shield of a cable. I have myself grounded. I will charge up that strip to approximately 2,000 volts, and then I'll ground the outer shell, which it represents the coax cable outer conductor. And you can see that if I move that conductor now by changing its position on Earth, I have taken and induced a charge in it. It's very difficult to get charges off of cables. Grounding one point or the other can transfer charge back and forth. This is why engineering has to be involved in procedures for connecting cables up to boxes. We said in the outline we were going to cover damage mechanisms. And to do that, we need to define again what voltage sensitive and energy sensitive devices are. Voltage sensitive is the most sensitive device and can be damaged by fields. And it's the one we worry about the most. The energy sensitive devices are fairly easy to protect them. The damage to devices by electrostatic fields will be covered when we explain what these devices are, and we'll show you that damage by direct discharge can come from charged surfaces. Voltage sensitive device, as we said, is the one that will be damaged by a field. You do not have to make contact with the device. A voltage sensitive device can be thought of as analogous to a string, and the tensile strength of the string is the failure of the gate oxide. It turns out that a voltage sensitive device is an unprotected gate oxide MOS device. There are not very many of these devices around, but they're the hardest to protect and the ones we have to make sure that they do not get through the system without proper protection. The gate oxide will not allow any charge to go through it. We said previously that if you had an induced field into this high insulator, you would develop a very small current through it, and a very small current through a high resistance will develop a high voltage, and you'll have a breakdown. There's a narrow range of this failure of the gate oxide, and the breakdown occurs in a very short period of time. Heat conduction is not a factor. The breakdown is analogous to a piece of string. We take a piece of string and we put pressure on it. It doesn't fail. I cannot fail it just a little bit. It either breaks or it doesn't break. That is the narrow range of a voltage sensitive device, and this can be caused by charged surfaces being brought near a device, and if the capacitance is sufficient to induce a voltage that goes beyond the breakdown of the gate oxide, the device will be damaged. The other type of device is an energy sensitive device. This device represents the vast majority of devices that are out in the electronic world. The energy sensitive device is a semiconductor junction, such as a diode or transistor, and MOS devices can be connected up to look like a semiconductor junction diode. The reason for considering a diode is that any device hooked up in this manner will let current go through it in the forward and the reverse direction. This is what makes it insensitive to electrostatic fields, because the device is damaged by heating of the junction when a vast amount of current goes through in a very short period of time. It's the applied energy that is similar to melting of solder that does the damage. The heat that is applied very rapidly exceeds the dissipation rate of the device. The device will rise to a temperature which will destroy the junction. The damage is related to the human body model HBM energy classification. And we can look at this device as being a piece of solder or a piece of metal, and it's the amount of heat we apply. If we take a very thin rod And we take a match and we strike it. Now we have a flame here, and we bring the rod. It's very small. It will heat up rapidly and even become red hot. If we take a larger rod and place it in there, it takes far more energy to heat this rod and bring it up to the melting point. That is what is the difference between the gate oxide and which is a voltage sensitive device, sensitive to fields, and the energy device, which is sensitive to a direct discharge, which is a rapid transfer of energy. If we look at some failures of gate oxide, we can see that this failure can be created by handling, because we can exceed the voltage range of the device. And we also can see that we've had damage in devices by improperly adjusted or ionizers that have very long pulse rates or have gone bad by putting out one polarity. You'll see the damage here shows a little melt zone, which may be hard to see on the video, and it pokes through the oxide either at the edge or in the center of the gate oxide of this device. This device was a 160 volt device, and it was able to be blown by handling, following all the procedures. The device was also able to be blown by a bad ionizer. This is why ionizers need to be certified by process control. Here is the protection circuit that we will do the demo on. We'll use our electrometer again, and we will bring a styrofoam cup down on the electrometer, and as you saw, that will raise the voltage on the electrometer plate, induce a voltage on it. We take it away, it'll come back to zero. Now when we connect up the plate of the electrometer to a neon bulb, and we apply the same induced voltage by placing a cup on the electrometer plate, it will go up to approximately 60 volts of the neon bulb. When you take the cup away, it will go in a negative direction, and we can do this repeatedly. The protection circuit's being exercised and the device is protected and not damaged. This is the demonstration of the protection circuit. I'll ground myself and take our styrofoam cup, charge it up again, and show you that it will drive the electrometer off scale. And now what I will do is take our protection circuit and connect it up to the electrometer. This represents a circuit between the input pins of a device or any protection circuit on a trace. And what we have here now is that this represents the transistor input pin. This represents the ground of the board that the transistor is on. And we'll take our cup and we'll go down here, and you'll see there's very little change in voltage. We will now go down to the 200 volt scale, and you should be able to see the 60 volt up and down charge change. My wrist strap just dropped out, or I didn't connect it. I will connect it up again and make sure the experiment is right. And you see, I can't drive it off scale. The minute I disconnect my protection circuit, I'm driving it far off scale. And that's why most electronic circuits at workstations, if you follow all the rules, will be protected, because you will always develop some tribocharging, but this circuit prevents you from damaging any devices. You still have to follow the rules of grounding yourself and proper packaging and handling. To understand how small these devices are, this little speck you see here is a IC, that integrated circuit that has many transistors on it. These transistors, for the most part, have protection circuits built into them. To give you a better view of this, you will see this chip with the little tabs on the end of it that are 5 mils across, and the little white spot coming across is a gray hair that is put on that, which is about 2.5 mils or 2.5 thousandths in diameter. You can hardly see the transistors, but you can see all the interconnecting circuits for this particular device. This is fairly old technology. Present-day technology now is down so small that you would not be able to view it optically. You'd have to view it with electron microscope. And these devices have gotten so small, though they've gotten more sensitive, the protection circuits have to be there and have gotten very strong to protect the devices. We're going to conclude with some demonstrations that we want you to take back to the workplace that are important for ESD protection. And it will also impress you on the awareness that you need to keep for protecting ESD sensitive products. I've grounded myself in wrist strap. I have a ESD glove on, which is dissipative or conductive depending on the brand. It will discharge something that you have a charge on, but it also will create charge on conformal coated or fiberglass circuit boards or a lot of other objects that you may touch. To show this, we have a radio here. It is on. It's turned off station, so you won't hear the station, but you will hear the charging going on as you rub this surface. Now, if we take a piece of metallized material and we take the Teflon material and charge it with the wool, you'll hear the wool also charges it like the glove. We will raise it off the surface there and bring the metallized bag to it, and you hear the discharge. We'll try that again. Whoops. You hear a series of discharges. Now we'll repeat the experiment with charging it, and we'll use a piece of dissipative material. This is pink poly material, and will come into the surface, and you do not hear the discharge that you do with metallized materials, to show that you need to remove the metallized materials from the workplace. We saw that an ESD glove would tribocharge Teflon, but it will also tribocharge the items in your workplace, as we stated earlier. Over here we are coming to an electrometer, and I'll check that we're at the 2,000 volt scale, and we are. And now, rubbing a piece of metal, we don't see any voltage. And if we charge the plate up to 2,000 volts, you'll see that it discharges fairly rapidly. If we take the metal electrode out and put in its place a metal electrode that's covered with conformal coating, and now we rub this surface, you'll see that we generate voltage very easily. And you can see the palm of the hand adding on to that surface generates a lot of charge. I wouldn't generate as much if I was touching a very small point. If I put a fiberglass board in there, we can generate charge also. And this is what the materials are made of in your ESD that you need to protect for ESD. We'll take a piece of wire, put it in our electrometer, and with my glove again I will show you that you can generate voltages on a 6-inch piece of wire. If I discharge it to 0, you think the charge has gone away. If I put my hand over it, you'll see the charge is coming back. Since the wire is small, we don't see a great change on this, but we can get 700-800 volts, and I can discharge it, 0 it, put my hand on the wire, and now the charge is coming back. To demonstrate this, you see that on the 200 volt range here, we are past 200 volts. So voltage-sensitive devices would have a real problem with this length of wire. We'll take an ionizer over here, and we will turn the ionizer on and watch the discharge rate. You're also hearing it on the radio, so I will shut the radio off. You see, it takes quite a while for it to come down. Ionizers can give you a false sense of security because they do not discharge as fast as the charge plate monitors indicate. It's taking quite a while to get below the 200 volt level. And of course, if I touch it in any way, with my hand, with an ESD glove, much worse, you're generating a lot of charge. So it is very difficult to prevent charges from being generated that will affect voltage sensitive devices. One of the things that's most often asked is how far away do you have to be from ESD sensitive product. This demonstration will give you a feel for the different types of discharge and the distances away. 1 meter rule was in the military early. It has been removed, but staying a good distance away if you're not grounded is a good practice. But when you're actually working on devices, we will take and show you how far away a charge can actually transfer itself to any material. I have the Teflon sheet here again, and it's sitting on top of the case of the power supply, which is grounded. And I will connect myself up to ground again for the wrist strap. That's just good ESD practice. And I will turn my radio on, put it off station, and the demonstration is going to involve this gold ball, which is a ping pong ball plated. There's a neon bulb in here connected to one end of it. The other end comes out to a rod which I'll be touching. I'll be holding it on this end, and I'll be holding it on this end, and we'll see the discharge coming off the sharp edge here, the small edge, and off the gold-plated ball. The Teflon is charged again by rubbing it, and as we said earlier, capacitance is an important factor in the amount of damage that can be done. In this case, as I lift the Teflon up, the field now is free to go to other objects because the capacitance has changed. And when I take the gold-plated ball and I approach the material, you hear an arc. That arc is a good distance away. That's an actual arc that can damage energy-sensitive devices and voltage-sensitive devices. If I repeat the experiment, and this time I use the very small end, and I come in, you should hear some discharges at a further distance out. That discharge is not as severe as the discharge off the gold-plated ball face closer. That shows you that at a distance, if you get corona or fields, you can damage a voltage-sensitive device from that. To show you the effect of capacitance now, we'll leave the Teflon on the surface that's grounded, and we'll bring the gold-plated ball near it again. Have to be very close to get a discharge. And you can see, picking it up, I'm getting discharge a long ways away. That's the change in capacitance. I can do it for the other end also to start it back at an even point. I'll go with the narrow point here, which is the worst case as far as discharging at a workstation goes. I'm about an inch away. So what this shows, about 11 inches out, 12 inches out, is the distance that a highly charged object will discharge to the circuits. So if you stay further than that distance away, you're going to be fairly safe for protection of devices. What we have talked about is the voltage-sensitive and energy-sensitive devices, packaging, the rules that you need to follow for grounding at ESD workstations. The voltage-sensitive device can be damaged by fields. They're the hardest to protect to. They need special consideration. The energy-sensitive devices can be protected by following all the normal rules. The types of materials we talked about was the metallized foil, the pink poly, and the metallized material. The foil material is the best shield, and for voltage-sensitive devices that need full protection, we package it in pink polyethylene, then we put the pink polyethylene inside the metal foil bag. That gives full protection. The metallized bag, as we've shown just in these last demonstrations, will transfer charge very rapidly, as will the metal foil bag. You have to be extremely careful and where you have those bags and to remove them in the workstation. The pink poly bag dissipates the energy in the material, discharges the charged surface slowly. That is the ideal material to have. If you follow the rules that we have set up here, we will not have a problem with electrostatic discharge damage of any of the components. The voltage-sensitive devices are going to take special care, special consideration, and we need to be very careful with those devices. Before we move on, there's one more issue we have to cover, and that's the issue of moving air. People believe that moving air tribocharges. The air does not have sufficient energy to cause ionization of a surface or charging of the surface. What we have here is a box that has a 100-pound weight on it with a closed orifice, and as you know, with the bicycle pump, when you pump up your tire, the air gets hot. But if it comes back to the same temperature as the temperature outside the box, the speed of the molecules in the box and outside the box are the same. In other words, the still air velocity inside the box is the same as the still air velocity outside the box, and it's a supersonic speed. The sum of the velocity is zero, because all the molecules are bouncing off of each other. The reason it supports the 100-pound weight is that there are more of them in here than there are out there. And because there are more of them in here, when you open the orifice, they come streaming out because they have a longer distance they can go before they bump into another molecule. But they're going at exactly the same speed. Therefore, they have as much energy stored in the velocity of the mass as they have out here. And this time, when they're going out through there, you feel that sum of velocities in one direction as air blowing onto the surface. But still, it's clear that from these two numbers that the energy is the same. Therefore, the gases flowing out of a nozzle, air blowing over a surface, will not tribocharge that surface. Since it doesn't tribocharge that surface, no electrons are lost or gained by that surface. And therefore, moving air is not a danger to any electronic devices. At Lockheed Martin, we use this electrometer system to measure the charge at the workstation to determine if there's any potential for damaging sensitive electronics. We do not use handheld field meters to survey insulators and other objects in the area. To demonstrate the unreliability of the reading that you get from one of these meters, the setup here has a Teflon surface that has a plate sitting on top of it, and everything is at zero. The meter is reading at zero. The meter is at the zero distance, or the 6-inch distance, which is correct for reading the voltage on there, at zero. And now we're reading approximately 1700 volts on the electrometer on a 5 picofarad capacitance, and the meter does not show more than 400 volts. You put it back again, and the meter changed very slightly. And we can see that there is a charge there as we bring the meter down, but it has to be at the correct distance to give the reading. Therefore, to really understand how much charge is on a circuit board, we use this electrometer system to measure the charge on the device itself so we can get an accurate reading and not misled by the potential damage that could occur in operations here at Lockheed Martin. If we look at direct discharge, we see that if we have a transistor type of device, which is represented by a junction, which can be a diode, field effect, if we have a direct discharge to that, whether it's damaged or not depends on the amount of energy in that discharge. If we have a charged surface here that is inducing a charge through the capacitance, the charge will run through this device. It won't be sufficient to hurt the device. With the field effect transistor, the MOS devices that do not have any protection, the gate oxide, if you take and throw an arc onto any pin leading to that voltage will be exceeded and the device is damaged. This case also, if you bring a charged surface near the capacitive coupling, if it exceeds the voltage of the device, you will damage it. Most likely destroy it because of the narrow range of voltage that it takes to cause damage. If we look at MOS devices, metal oxide semiconductors, that most of the computer chips are now, and a lot of the other electronics, there's protection circuits. These protection circuits are represented by diodes, and any field induced onto these devices will just run current through the diode protection, and the gate oxide voltage will not be exceeded. The device is protected. Lockheed Martin has several pieces of information concerning ESD. The first brochure here is our basic awareness training that's given to all the people that take ESD awareness training. The second item is a list of untrue statements. This has been created by the Lockheed Martin Material and Process Control Engineering Lab, and these statements are some of the common misconceptions that are in the industry. And people can call our department to find out what is going on with the different statements if they need to have them elaborated. The other piece of information that explains what is going on here at Lockheed Martin in way of controls and the damage that can occur when you have ESD problems and no controls is this Lockheed Martin Electrostatic Discharge Handbook. And there is a sheet of information here in how to order that. If you call Process Control Engineering, we can give you that information.
An electrostatic protective environment is an area in which people can move around and move electrostatic discharge-sensitive components around without fear of damaging the components with ESD. This can only happen if everyone in the area follows specific electrostatic discharge preventive procedures. It's necessary for all people who come into the ESD protective environment, whether employees or visitors, to abide by the rules for the protection to be effective. In this lesson, you'll learn about the electrostatic discharge protective environment, footwear and garments which can reduce the danger of electrostatic discharge, and ESD protective workstations. In an electrostatic discharge protective area, all static electricity in the area is controlled and doesn't present a threat to electrostatic discharge sensitive product. Everybody and everything is at what we call ground potential, meaning it has no significant static electricity on its surface. To keep everything at ground potential with no static charge, entrance to the area is controlled. Protective garments are worn when required because the components being handled are very sensitive to ESD. All workstations, furniture, and equipment are ESD protective. Static generating personal items made of plastic like picture frames, radios, and holiday decorations are eliminated or controlled. Because everything in the environment is at ground potential, ESD sensitive product may be moved around without worrying about damage from electrostatic discharge. Requirements for an ESD protective environment may vary from company to company. But typically, before coming into one of these areas, you need to put on protective shoes or shoe straps and test them. Leave extra street clothes and shoes in your locker. Put on ESD protective garments before entering the ESD protected area. And read warnings before entering the area and do what they say. These instructions will require you to test your wrist strap and footwear before entering the area. In the ESD protective area, there will be a static dissipating floor. This special kind of flooring produces very little static electricity when a person walks on it. It also provides a ground path for people wearing static dissipative footwear, for mobile equipment which has conductive wheels, and for furniture with conductive wheels or footpads. Because of its static dissipating nature, the floor allows people and equipment to move around and stay free of static electricity. A static dissipating floor, though, won't provide a ground path for you if you're seated. You must take other precautions while seated, such as wearing a wrist strap. Even when walking on a static dissipating floor and wearing static dissipating shoes or shoe grounders, you should wait 2 seconds before touching an ESD sensitive component. This gives any static charge on you a chance to drain away. Carts and other mobile equipment with conductive wheels will stay at ground potential when used on a static dissipating floor. The floor, however, must be kept clean. Dirt can't be allowed to build up on it, and the floor should also be free of litter, trash, and packaging materials. Walking is one of the most common ways of building up a static charge on yourself. Even if you're walking on a static dissipating floor, you'll build up a charge unless you're also wearing static dissipating shoes. If you're wearing insulating shoes, like those with rubber or plastic soles, you'll build up a charge on the shoe and on the rest of your body. Then when you touch an electronic component, you will create an electrostatic discharge which can damage the component. Even after the discharge, you'll start building up another charge on your skin with your very next step. Wearing static dissipative shoes helps prevent the buildup of a static charge on your skin when walking. When you wear static dissipative shoes and walk on a conductive or dissipative floor, your skin will stay at or near ground potential. Still, after you stop walking, you should wait 2 seconds before picking up or putting down an electronic component. While static dissipative shoes are considered more effective, shoe ground straps are another way to reduce the buildup of static electricity on your skin when walking on a static dissipating floor. You may also hear shoe ground straps called heel grounders, toe grounders, or shoe grounders. The ribbon must be placed inside the shoe and under the foot. When using shoe grounders, you must wear them on both shoes. As with static dissipating shoes, you should wait 2 seconds after walking before picking up or putting down a component. If you work around an exposed electrical hazard up to 250 volts, it's important that your shoe grounders have current limiting resistors. Never use a shoe grounder that doesn't have a current limiting resistor near an exposed electrical hazard. There can be a danger of an electric shock. Do not wear shoe grounders at all if you work around exposed hazards over 250 volts. You should test your electrostatic discharge protective footwear at least once a day at the beginning of your shift. Hold the footwear tester with your hand while standing on the test plate. Test each foot separately. If the yellow light comes on, you are not wearing good footwear or your footwear is on wrong. Check to see what the problem is and correct it. Don't go into the ESD protective area until the green light on the tester comes on. If the red light comes on, your shoe grounders are too conductive. While you are not an ESD hazard, you cannot work around exposed hazardous voltages. If you are using leather-soled shoes for ESD protection, test them at least twice a day. The static control properties of these shoes change with humidity levels and the condition of the person wearing the shoes. They are not reliable in dry climates. Static electricity can build up on your clothes and cause damage to ESD-sensitive components, even if your skin is at ground potential. To avoid this source of static electricity, you can wear static dissipative clothing such as a smock or lab jacket. Static dissipative garments are not always needed when handling electronic products. Only the most sensitive components require their use. These should be kept fully buttoned or closed at all times, and the cuff should be in contact with your skin. Static protective cleanroom garments should be worn according to established gowning procedures. ESD protective workstations are an essential part of an ESD protective environment. There are several features of the workstation which control and eliminate static electricity. The entire work surface is static dissipating. It provides a path to ground. Storage surfaces for unprotected ESD-sensitive material are static dissipating. The wrist straps are connected to an ESD common point ground. All unnecessary static generating items are eliminated, and necessary static generating items are controlled with topical antistats, ionizers, or by being kept at a safe distance from product. Finally, a grounded floor is provided if necessary. There are a number of procedures to follow when using an ESD protective workstation. First of all, always wear your wrist strap and be sure to connect it to a common point ground. Remove all non-essential static generators. For those static generators that can't be removed, control them with ionizers, topical anti-static treatments, or by keeping them safely away from sensitive components. And finally, regularly audit the workstation to be sure correct procedures are being followed. There are other kinds of ESD protective workstations which you should know about. One common one is the stand-up process workstation. This is used when it's not practical for a person to sit because of the kind of work that is being done there. Examples of a stand-up process workstation are a wave soldering machine, an aqueous cleaning machine, and a packaging workstation. Proper procedure for working at a stand-up workstation includes all of the rules you have already learned for working at a general-purpose ESD protective workstation. In addition, you will need to wear static dissipating footwear, such as shoes or shoe grounders. Test the shoes at least at the start of each shift, and test the shoe grounders at the start of the shift and after the mid-shift break. For this footwear to be effective, the stand-up workstation should be on a certified static dissipating floor or a grounded dissipative floor mat. You must wear a wrist strap or other skin grounder, have it connected to the common point ground when you are seated, and test it regularly. At a test equipment workstation, product is tested manually or automatically. The test heads may be sensitive to electrostatic discharge. When working at a test equipment workstation, follow all general workstation rules. All work and storage surfaces should be made of static dissipative materials or laminate. It may be necessary to add additional dissipative surfaces and ESD common point ground terminals. Wear your wrist strap at all times and have it connected to a common point ground. Ionization is the best method for controlling static electricity on the test heads themselves. Topical antistats are not good for this purpose. Finally, you should be careful to practice ESD protective procedures even when product is not present. High-voltage workstations present unique issues in the control of electrostatic discharge. Generally, safety experts consider a workstation to have hazardous potential if it has open, exposed metal parts, with the possibility of accidental contact at over 42.4 volts peak AC or 60 volts DC, and capable of supplying a current greater than 0.7 milliamps peak or 2 milliamps DC. Examples of high-voltage workstations include high pot testing, power conditioner testing, video monitor testing and alignment, and uninterruptible power supply testing. High-voltage non-hazard workstations have no exposed metal parts where you could make contact with the high voltage. Interlocks, insulating barriers, and other devices are used to ensure that you can't make contact with a high voltage. Electrostatic discharge controls cannot be abandoned because of the presence of hazardous voltage. In situations where personnel cannot wear wrist straps because they may experience electric shock, static electricity must be kept under control. Of course, personal safety requirements take priority over ESD controls. High-voltage workstations should be made of materials that don't generate static electricity, but are relatively good insulators, such as wood. Personal grounding devices such as wrist straps and shoe grounders with current-limiting resistors can be worn in the presence of hazardous voltages below 250 volts. You may not wear them or ESD protective garments around open exposed hazards with the possibility of accidental contact which exceeds 250 volts. Your personnel safety manager may change these rules depending on the work conditions in your plant.
In 1937, the Atlantic crossing of the airship Hindenburg ended in disaster. While docking in Lakehurst, New Jersey, the 200,000 cubic meters of hydrogen gas explosively caught on fire. While officially unconfirmed to this day, the cause was a well-known physical phenomenon, the spontaneous discharge of static electricity. This phenomenon comes about quite simply. If two initially neutral objects come into contact, there is a charge transfer, which then remains after they are separated, distributing itself over the entire surface. On contact with other conductive objects or grounding, the charge suddenly escapes and can possibly arc over shortly before contact. In the Hindenburg case, a spark presumably ignited the highly explosive gas. Back to the present. In the age of microelectronics, failures and interference caused by static discharge have gained dramatically in significance. Because of their constantly decreasing geometry coupled with the increase in their integration density, microelectronic components have become more and more sensitive to this discharge. The official designation for this phenomenon is ESD, electrostatic discharge. It's the term we'll be using from now on.
Because we believe that primarily highly integrated ICs are endangered, we often overlook the fact that simple components like optoelectronic devices or diodes or even power semiconductors can be destroyed by ESD.
Before we began implementing ESD protective measures, we had plenty of failures. This is an unacceptable situation when cost-intensive components are being used.
Reliable ESD protection is only possible when everybody involved knows where its causes and effects are located. In production practice, this means protective measures from wafer production all the way to back-end and component testing, from development and assembly to the delivery of the finished piece of equipment. Charges are generated and circulate everywhere. We all know this famous crackling sound when we take off a sweater. A few examples should sensitize us to the number of charges that might come about every day. By the way, we can only feel discharges from voltages of about 3,000. Sometimes we don't even notice when a charge is generated. Or inappropriate materials like these non-conductive shipping tubes are used. Even the electrostatic field of an unreleased monitor can lead to uncontrolled ESD stresses. To clarify this point, one final example. When we touch an electrical circuit with our bare fingers, the result has the same energy density as a lightning bolt slamming into a tree. The damage to a component is quite similar. Charred connections, burned and broken surfaces, and even the remnants of explosions. This is why Siemens developed HLSEP, a complete strategy for external ESD protection based on international standards. The objective is to avoid ESD failures, from wafer production all the way to delivery to the customer. The most important factor here is our awareness, our heightened sensitivity to ESD events, followed by so-called internal protection. This is ESD hardening of the components through design procedures and specific ESD tests, as well as external protection to reduce ESD stresses organized by HLSEP. The basic prerogative involves handling the components in a specially equipped ESD protective area, EPA for short. This is clearly identified and may only be entered by properly equipped and trained personnel. The EPA is based on the fundamental principle of only allowing charges to dissipate under controlled circumstances to avoid potential differences. As early as the planning and construction stage, we have to see to it that the floor is grounded and made of dissipative material. The shelves and work surfaces have defined ground resistance ranges to make sure charges will not dissipate either too quickly or too slowly. Movable storage equipment is also fitted with groundable wheels. The same principle applies to chair wheels. The covers and upholstery are also made of dissipative materials. The use of highly chargeable insulative materials, especially in clean rooms, is often unavoidable for process reasons. They can be neutralized not by grounding, but rather only through the use of an ionizer. One highly sensitive area, for instance, is mask technology.
Throughout the production of semiconductors, there are any number of procedures which might result in ESD damage, such as testing ICs while still in the wafer stage, bonding the connecting wires, trim and form, or checking the component with attachable electrodes.
Now let's turn to the main problem, the people who work here. EPAs may only be entered with dissipative released ESD footwear. It is also important to keep the coat constantly fastened. Static charges also have a helpful side effect. They can be locked in or shielded. If the coat is unfastened, the electrostatic field of someone's personal clothing might exert a direct influence on the component. In special cases, instructions may be given to wear dissipative finger cots or gloves. The most important item here, however, is the wrist strap, which should always be tested before entering the labeled EPA. As should the ground resistance of the footwear. A heel strap like this one is available for visitors.
Of course, we sometimes have problems observing these regulations, but daily routine causes even the most reliable individuals to forget the occasional test procedure.
To prevent carelessness from gaining the upper hand, especially in large plants, the gate only opens after the tests have all been passed. When handling components, even in laboratories, some fundamental rules should be strictly observed. For example, outer packing should be torn open outside the EPA until the ESD label is visible. Connect the wrist strap, then cut open the adhesive sealing material. Do not tear it open. Only approved and properly labeled packing and filling material may be used in the EPA. In other words, no highly conductive materials like styrofoam. Components being unpacked should only come into contact with dissipative materials to avoid hard discharges. If you think this will eliminate every hazard, you're wrong. Remember friction, which, as this experiment demonstrates, can come about at any time during a fully automated manufacturing process. This is why only suitable packing should be used here as well. In production, we have to use defined dissipation, ionizers, and the proper selection of material to keep ESD under control right down the line. Even so, a component charged by unpacking or sliding along the material track might discharge on contact with a metal machine part. This is why modern assembly equipment uses the pick-and-place principle, virtually without sliding. The skyrocketing development of manufacturing technologies calls for ongoing research and testing, because practicable solutions can only be found in a balance of potentials inside an EPA. This is why the Siemens Semiconductor's ESD laboratory is optimizing the resistance of work surfaces, tools, machinery, and packing materials. The widest variety of materials and shapes is subjected to ongoing testing. Precise results call for high precision and the devotion of a great deal of time to the measuring process. Several environmental factors such as humidity or the selection of test methods also have an effect on results. Incidentally, should components need to be shipped for failure analysis, they should of course also be provided with ESD protective packing, so that no damage caused en route can obscure the actual failure to be tested. This is the only way a precise failure analysis will be possible. Thoroughgoing ESD protection can only be practiced with the active participation of everyone involved. Daily routine often harbors a great hazard. This is why ESD awareness and a full knowledge of physical causes and their effects are so crucial. Moreover, every ESD staff member is responsible for testing his grounding aids, such as wrist straps and footwear. In addition to the HLESD coordinator and the local ESD representative, Siemens also has an abundance of proven procedures and technical periphery at its beck and call to prevent ESD damage. Customers and other companies are also able to take advantage of this know-how and technical support. All Siemens staff members can access an ESD online training program on the intranet, where the latest test results from the ESD laboratory are also made available worldwide.
Our latest figures prove that failures rapidly decreased after Siemens ESD training and the thoroughgoing implementation of ESD protective measures.
The minimization of dimensions in microelectronics is steadily on the move. This means ESD sensitivity will keep rising, despite protective measures inside the devices. This is why the future development of ESD protective measures at Siemens will always be one step ahead of progress in production technology.
It begins silently with calm, fleecy islands moving across the sky's blue sea. The wind begins to whisper as more nimbus billows join the others in the now cloud-congested atmosphere. The clouds churn against each other until they create static electricity, erupting in the form of lightning bolts. This earliest and simplest form of electricity is the result of only two elements: chargeable bodies and motion. In the case of lightning, the clouds moving together in the sky are the chargeable bodies. People are chargeable bodies too. Just by walking, we can generate thousands of volts of static electricity. Static electricity is everywhere. Unfortunately, it causes problems such as the dreaded static cling, which can affect your clothes. But of greater concern is the fact that static electricity spells trouble for some electronic parts. When it's released into an electronic device, it's known as electrostatic discharge, or ESD, and it can cause irreparable damage to a component. We can think of static electricity as a tiny lightning bolt looking for some place to go. The lightning bolt plays havoc with an electronic part by traveling from a charged surface with a voltage potential into the actual part. If it moves through a device which can't handle this voltage movement, the device can be stressed, damaged, or even destroyed. The purpose of this program is to help you guard your components against these menacing ESD bolts. Quality is the key to success in the electronics industry, where there are many causes for product failure. It's estimated that ESD could account for as much as 10% of these blunders. And although we've eliminated a lot of the problems responsible for product rejects, we haven't been able to eradicate ESD, and we probably never will. But we do have the necessary tools to reduce the number of ESD damaged products to a negligible amount. And because we're removing at least some causes for product failure, it's becoming easier to pinpoint devices which have been zapped by ESD. Quality-minded personnel find it challenging to protect components from ESD catastrophes. These people realize that the consequences of ESD damage can be severe, especially when a crippled part is unknowingly put into service and fails later at the worst possible moment. For instance, some ESD-sensitive devices are used in life support systems, not only for hospital patients, but also for astronauts in outer space. Imagine how you would feel if one of your components or assemblies became defective in one of those situations. In fact, a static spark is blamed for the capsule burnout, which killed 3 American astronauts in 1967. You as consumers also are plagued by ESD damage. Sometimes on a sizzling summer's day, your car goes on the blink. You miss an important call when your wireless telephone fails. You overdraw your checking account because your electronic calculator misfires. You're robbed because your burglar alarm malfunctions, or worse yet, your house burns down when your smoke detector breaks. The culprit in each case could be an ESD damaged part. The magnitude of the static charge we generate hinges on several factors: humidity, the types of materials involved, and how rapidly they're separated. Generally, ESD becomes a more serious problem on low humidity days, when the lack of moisture permits a more rapid static charge buildup. The charge also depends on the kind of material generating it. Common plastics and other synthetic materials cause the most trouble because they're insulators and prevent the free flow of electricity by trapping the charge on the surface. Paper, cotton, and wood are considered somewhat neutral because they tend to absorb small amounts of moisture from the air. This makes them poor insulators and somewhat anti-static. Component damage increases with the voltage level, and it doesn't take much to create a significant charge. On a dry day, we can generate a static field of more than 100 volts by just the slight raising of an arm. So it's not surprising that during normal, everyday activity at an unprotected workbench, you easily can generate 6,000 volts or more. The ESD threat looms everywhere in electronic work areas. Floors, chairs, work surfaces, packaging materials, plastics, and papers all give rise to static electricity. But you pose the greatest danger to sensitive electronic material because the human body can generate the biggest static charge of anything likely to come near these devices. The ESD problem does not end at the workbench. it can strike at any time during the life of the part. Even when a component is installed on a circuit card, it still is vulnerable to ESD. That's why everyone involved in the handling, installing, testing, maintaining, shipping, and storing of sensitive electronic hardware must be made aware of this lethal threat to components. ESD is a tricky matter. Most of the time it can't be seen or heard. You can't always feel ESD either, because people usually don't sense a discharge until it's greater than 3,000 volts. Sensitive devices also can be stressed or damaged even without physical contact, a phenomenon similar to combing your hair on a dry day. Your hair stands up without being touched by the comb. Until recently, components could take a discharge of several hundred volts before becoming injured. But today, the trend is toward miniaturization of devices, and some of these shrinking parts are sensitive to only 50 volts or less. For example, this integrated circuit, or IC, is composed of many transistors on a single silicon chip. As technology allows more and more transistors on IC chips, each transistor becomes smaller and therefore more susceptible to that ESD lightning bolt we mentioned earlier. Although there are many transistors on an IC, it could become useless or disabled if only one transistor suffers ESD damage. We can see the move toward smaller components in such items as heart pacemakers, electronic telephones, handheld calculators, avionic control systems, and electronic test equipment. Since miniaturization is vital for modern-day electronics, we expect the ESD threat to become even more acute in the future. It's important to understand that electronic devices are vulnerable to two primary failure modes: catastrophic and latent. Catastrophic failure means that ESD damage has ruined the part completely. This kind of damage usually is detected in the testing stage. The devices that succumb to latent damage add insult to injury. These parts pass inspection because often the damage is impossible to detect, even by microscopic scanning and electrical testing. We can refer to devices with latent defects as the walking wounded because they may be put into service and later become intermittent or fail completely. We can better understand what ESD does to a part by taking a tour inside of this MC1741 general-purpose bipolar operational amplifier. This integrated circuit was subjected to a static discharge of approximately 4,500 volts. Both inputs to the device were damaged. With visual inspection under a high-power microscope, you can see the emitter and base junctions of both input circuits. The base metallization is burned open on both inputs, and mass transport or zap mark is evident across both the emitter-base junctions. As you can see, the upper junction appears more severely damaged than the lower junction. However, both are damaged beyond use. Now let's look at the measures you can take to avert this ESD death blow. Major elements involved in an ESD protection program are human grounding devices, static-free grounded work surfaces, and special packaging methods. A properly grounded wrist strap is your first line of defense against ESD. So think static as soon as you arrive at your workstation. This will remind you to immediately put your wrist strap on and test it to ensure that it's in good working order. This handy gadget will remove the charge from your body when it's connected to ground and, if you wear it properly, on your bare wrist. Taking off your wrist strap also should be the last thing you do before leaving your workstation. For areas where wrist straps are impractical, grounded heel straps or special footwear are essential. The heel straps must be worn correctly and used in conjunction with conductive flooring and floor mats. The next part of an ESD safe workstation is a static-free work surface such as this grounded conductive tabletop. It helps control static because the charge from any conductive or anti-static material placed on it will be drained to ground. We also have two main types of packaging materials which protect parts from ESD damage. They're called anti-static and conductive static shielding. Anti-static packages generally are pink or blue in color. They help create static-free environments because they don't generate charges. On the other hand, they don't provide static shielding. That's why you'll see anti-static materials being used to cushion or enclose electronic devices inside conductive static shielding containers. Anti-static materials differ from common plastics due to an anti-static compound which is mixed in when the product is first formed. Anti-static material doesn't give off particle contamination, so it's found mainly in clean room environments. However, care must be taken to limit the number of times this material is reused, because use and time reduce its non-charging capabilities. The other form of packaging material, conductive static shielding, also does not generate a charge. But in addition to its anti-static properties, this material has the ability to shield devices against static. In other words, this conductive static shielding packaging material will not create a charge, and it also protects what's inside. This material is considered a static shield when it completely envelops an object. When a package is properly closed, it can be handled by anyone and shipped through any type of environment. But when this package is opened, it must be at a protected workstation by a person wearing a wrist strap. There are three varieties of conductive static shielding material. One is black in color and depends on conductive carbon particles. But this black material is not used in clean room environments because it can shed carbon particles and cause contamination problems. The second type is composed of transparent metal film sandwiched between two layers of anti-static plastic. A third kind of conductive static shielding material is an opaque metal bag with or without a non-conductive outer layer and an anti-static inner layer. If you're in a situation where you're not sure what kind of ESD packaging material to use, just remember this simple rule. Put anti-static material next to the sensitive part, and then place conductive static shielding around it. However, anti-static material isn't found only inside conductive static shielding material. It covers assembly travelers and work instructions. We also utilize it to package non-sensitive devices to make them acceptable for static-free work environments. Another precaution you can take to make your work area secure is to eliminate the use of plain plastic and synthetic items. Even if you're wearing a wrist strap at a protected workstation, sensitive devices should be kept away from common plastics, clothing, and hair. So don't wear long sleeves unless they're covered by a static dissipative smock. It's difficult to get rid of all plain plastic objects, but those necessary for your job can be made safer. Room-sized and localized air ionizers neutralize static charges in hard-to-reach places by providing constant streams of ionized air. Air ionizers also are used in areas where you have to have synthetic items. For example, air ionizers are a must when tape is used to mask printed wiring board assemblies. Topical anti-stats, when sprayed on synthetic objects, will also reduce their ability to generate static. But the process must be repeated as it's only a temporary solution. A variety of other products, such as special smocks, floor finishes and chairs, static locators, and canvas document holders, also are manufactured for static control. Now let's see if you can spot the gross errors people can make when dealing with ESD-sensitive devices and assemblies. These mistakes are expensive. The cost of ESD damage increases dramatically with the time it takes to discover a damaged device. If a defective part reaches the customer, the price of ESD damage is staggering, about 100 times greater than if it's caught at incoming inspection. But we can't put a price tag on one serious implication of ESD: the loss of an electronic company's reputation for quality. You control the destiny of the electronic commodities you're working on. That's why it's crucial that you put pride in your work and take the defensive steps we've demonstrated today. The marketplace is demanding more product reliability. As a result, knowledge of ESD control methods is vital for everyone in today's high-technology industries. Remember, your company's reputation for high-quality electronic products rests on your shoulders. So we're depending on you not to give us any static.
I'm Greg Peterson of the Materials and Processes Laboratories at Anaheim. You've seen a video on the general principles of ESD control, and now we'll learn about how those principles are implemented by our Anaheim site General Process Specification AAO 117-008. This specification requires that all personnel designing or handling ESD-sensitive items or supervising or monitoring those functions must be certified and have recurrent training. Next, the specification requires that personnel be protected from electrical shock. And to do that, we use a resistor in the wrist strap cord. Now, you've seen in an earlier video that the wrist strap is used to prevent the buildup of voltage on the operator's skin. Now, if the voltage builds up, the operator can zap a part with an electrical discharge, much like you would zap a doorknob on a dry day. To make sure that the wrist strap is functioning properly, we use continuous wrist strap monitors, as you see here. Now, when the wrist strap is plugged into the monitor, an alarm sounds unless the operator is properly grounded. And now John Collier of the M&P Labs will explain more about electrical discharge and the wrist strap monitors.
Hi. We're going to demonstrate how devices or static sensitive items can be damaged by discharges, and we're going to use two instruments. This is a pink static meter, such as you have in your areas, and this is a static event detector. The static event detector acts like a real device sensitive to 100 volts, such as a MOSFET. Now if we'll zero in on the meter, and you'll see that when a static voltage approaches the front of it, namely a field, we'll see the needle move. Now, that's all we need to know at the moment. This static event detector, as we zero in, consists of two parts. There's a base, which would be analogous to the substrate case lead of a MOSFET, and there's a cover, which would be like the gate lead of a MOSFET, for example. And when a voltage differential of more than 100 volts occurs suddenly between the case and the body, this little window will turn red. Now for the rest of the demo, you'll be seeing the static meter and the static event detector in my hands close up. Now we see the meter, and I am bringing my hand near it, and I'm stroking my feet on the floor. I am not wearing a wrist strap. You'll see I'm generating a high voltage. And now, looking at the static event detector, zero in real close. When I touch it, you saw the window turn red. Now in the first test, I had no wrist strap. This time I'm wearing a wrist strap, but it happens to be a bad one with the conductor broken inside of the insulation. So, as you see, with a bad wrist strap, and I wouldn't know it was bad if I hadn't tested it, I'm getting very large voltage on myself. And now if we'll look at the static event detector, and we will touch it, once again, it's been tripped. Now I'm wearing a good wrist strap, and if you'll look at the needle on the pink meter, you'll see that there's no motion. And zeroing in on the static event detector, I can touch it all day long and never trip it. The window stays white. This time I'm wearing a wrist strap with two conductors connected to a continuous wrist strap monitor, and when either of the conductors fails, the monitor will alarm. But interestingly, now, by the way, you will notice the pink meter is showing no needle movement as I shuffle my feet because, of course, I'm grounded. The interesting thing about the continuous monitor is if the conductor should fail in one of these wires, the monitor will alarm, but you will still be grounded. Now I'm going to disconnect one. You'll hear the monitor alarm, and you'll see that the needle still doesn't move when I shuffle my feet.
When an ESD-sensitive item is not in a static safe workstation, not shunted, or not in transit and being closely watched, it must be kept in a protective package. We use a so-called Faraday cage, which includes aluminum foil. The following demo will show why a pink poly bag is not adequate.
Hi. For our demonstration on static protective packaging, we'll once again use the pink meter, as you saw before. We'll once again use the static event detector. And now as we zoom in, we're also going to look at two protective bags. We have the familiar pink poly bag, which you can see through, and we have the foil bag, which we require as the outer protective covering. Here we see the static event detector again, and I've shunted the lid or cover to the base. This represents a device with the lead shorted, and such a device is by and large protected when it's out of a static safe workstation. Now again, I'll shuffle my feet and I'll touch the static event detector, and try as I may, I cannot trip it and turn the window red. Here we see the static event detector inside of a pink poly bag, and this time, without a wrist strap, I'm going to generate a charge on myself and touch the bag over the static event detector. And the static event detector has been tripped, turned red. You'll see it more clearly when I empty it out of the bag. There it is. Now, we just saw the static event detector was tripped inside of a pink bag. So now we're going to try a Faraday cage foil-containing laminate bag, as we are required to use. And I'm going to put the static event detector inside of it, slide it in there. Okay, now I'm going to remove my wrist strap, and I'm going to try real hard to trip the detector by touching it. Okay, and now we'll empty it out of the bag And if you'll zero in, we'll see that it has not been tripped in this case. The Faraday cage bag has protected it.
But discharges are not the only threat to ESD-sensitive items. Static fields can also damage unbagged devices, so we have rules to stay a safe distance away from surfaces that can radiate a static field, as the next demo will show.
Hi. In this last demonstration, we will again use the pink meter and the static event detector, and this time we'll use a piece of polystyrene foam or styrofoam, which as we zero in, this is a material which is definitely banned from workstations, and you'll see why. For the rest of this demo, the camera will be zooming in on these items in my hands. Here's the static event detector again. I'm holding it by its base, and now a piece of highly charged polystyrene foam will be brought up to it. And as you see, the detector was zapped by an air discharge through a considerable amount of space. The polystyrene foam never touched it, and in fact, static fields will damage devices at a distance in a similar manner.
At this point, we have the ESD-sensitive parts bagged when they need to be, static fields minimized, and people grounded, both the operator and visitors. But we still have to ground the workbench surface. This is done by a buried conductive layer in a hard laminate, or in this case, by a soft static dissipative mat, which is connected to ground through a ground wire at the laminate grounding lug or the mat snap. The M&P labs certify all benches and other workstations, such as ovens, for correct grounding and apply a certification sticker. Connections must be secure with no clips on wires or alligator clips. Well, I've covered the highlights. For other details, such as correct wearing apparel, you'll be reading the specification. Also, you'll be practicing QA provisions of the specification, such as scanning your workbench for dangerous fields with a static meter. In the future, or maybe by the time you see this video, we'll have continuous static field monitors that beep when a charged surface, such as a common plastic, enters the workstation. This concludes our brief lesson, and thank you for watching.